Thanks. Now, welcome everyone. As already said, name is Manuel Pöll. I'm from the Institute of Networks and Security at the Johannes Kepler University Linz. And our publication and the presentation will be about how we analyzed the reproducibility of the Android open source project, short AOSP. To give you, this is of course a team effort. There were many people involved, most notably my co-author Michael Roland, but many other talented folks. And a brief outline is essentially that we're going to talk about the motivation in a very brief fashion. I will introduce the Android open source project and its significance and why reproducibility is especially important there. And finally, we are going to look at how we automated this process and the findings that we actually had. So, to get us started, can you trust software? That's, of course, a big question. And in order to tackle that, we really need to look at the software supply chain. So I brought with me here a very simple software supply chain visualization where we start out over here with some source code, which we build. It is then distributed via some means or packaged up in some way, and finally arrives at the end user that actually runs the software. So in the very past, we had crude approaches to this. For example, an average user will go to the internet, download some arbitrary binary and run it. That's, of course, from a security point of view, quite bad. Thankfully, we have made quite a bit of progress. So by now, we see that a lot of software is written either as open source or we have some reputable software vendor behind these projects. So you can trust that at least people writing that software are not doing completely malicious things. Then again, we also have package managers and software and app stores that allow us to distribute software in an authenticated fashion. That helps us by bridging the gap over on the right side here. But what I'm going to focus on today is actually something else. I'll focus on the step between source and the build process and the binary artifact that we arrive from that. That gap between source and binary artifact is what we are going to look here today. Now, the problem with this is mainly that building software nowadays is a very complex undertaking. We have many tools that are involved in the software building and packaging process. It has been noted, this is actually quite a long-standing problem. Famously, Thomson already noted in 1984 in Reflections on Trusting Trust that if you cannot trust your compiler and everything that it depends on, then ultimately you cannot trust the software that comes out of that. So that is not just a long-standing problem, that is unfortunately still today a very relevant problem. We have seen quite a few software supply chain attacks, most notably the SolarWinds attack, where the SolarWinds build system was compromised, resulted in quite a large-scale security incident that spread over numerous countries, many in the US as well. How do we tackle that? Well, that's where reproducible builds come in. Reproducible builds are essentially a two-step process. First, you need a deterministic build system as a prerequisite. This deterministic build system essentially turns the build process into a mathematical function. For a fixed input, you perform the build process and you arrive at a fixed output. And as long as you don't change the input, it should never change the output. That's the first part. However, that alone is not quite sufficient. You also need independent builders. You want to have multiple parties that build the software and then perform a comparison. And only if multiple parties arrive at the same output, you can be certain that the software was not tampered with in that crucial gap between source and binary artifact. So Reproducible builds come with their own unique challenges. We have several types of metadata that can get bundled into an artifact. For example, timestamps and build paths are commonly inserted at some point in time, but most of that is just an engineering challenge that can be tackled and solved. But some aspects are more tricky. For example, cryptographic signatures are a difficult problem, which I'll come back to later. What did we actually look at? We looked at the Android open source project, the open source portion of Android specifically, because Android is quite an important and relevant target. It runs on billions of devices, and therefore it is highly relevant to achieve a secure system there. So Android itself actually is, from a developer point of view, a very complex software project. It has a ton of tooling involved. And ultimately, the output of the Android open source project build process are partition images that one flashes onto their devices. And the first question one has to ask themselves, what's the official stance on reproducibility? And currently, Google does not state reproducibility to be an official goal as of yet. However, they have an upcoming migration to the Basel build system, which does then include hermetic and deterministic builds as stated goal. So, in order to get started with an analysis, we obviously need some reference. We need some base that we compare against. And that's where our sources of reference images come in. First of all, we have the generic system images that are sourced from the Android Continuous Integration Dashboard. We call these simply the generic builds. Second, we have factory images from Google that are being flashed onto the Google phones. Nowadays, these are the Pixel devices. Previously, these were known as Nexus devices. Specifically, we looked at the following questions. First of all, we wanted to know if we take AOSP and perform a build of it and compare it against the result that Google arrived at. Are these equivalent? Are these reproducible? We have found that to be not quite the case, but we are actually very close. So the next follow-up question obviously becomes, what are these differences? Can we quantify them? Can we qualify them? And finally, since we saw that AOSP by itself is in a quite good state in terms of reproducibility, we went ahead and actually looked at the factory images, the device builds. The crucial point here is that Google actually uses a build target that is not entirely public. They have related build targets that are public, but the ones that Google uses are slight deviations. So technically, with this last one, we are not investigating reproducibility per se, but doing a comparison between the open source state and the state from Google. Now, we did all of this via a simple automation framework, which we called Simple Opinionated AOSP Builds by an External Party, short SOAP. We start out by retrieving the source code, building AOSP as is suggested by Google. We also obviously retrieve the reference images, the binary artifacts from Google. And these artifacts then, both artifacts then move on into a separate environment, into a separate Docker container, where we first do some pre-processing on these images and finally perform an analysis with the Diffoscope tool. That is a tool from the Reproducible Builds initiative that allows to do recursive difference analysis. So if you had, for example, a zip file, it would look into that zip file and compare the entries in there. Out of this entire process, we then get reports that are detailed in terms of qualitative reports that allow us to look at specific causes, but also we perform further processing into metrics that we use to derive a quantitative view on this topic. Now, going into a bit more detail and some specific remarks on what are our goals and non-goals. There are obviously others that have tackled Android and building it, and it's important to note that we are really looking to do, we're really looking to follow the guidelines from Google on how to build Android as closely as possible. So we are not trying to do a new distribution as would be the case with Graphene OS or Lineage OS. We are really trying to do Android stock as it is meant to be by Google. Second, for the analysis, we had two primary goals. We wanted to both quantitatively analyze the reproducibility that allows us to do longitudinal studies and look at how things evolve over time, but also on a qualitative level, because we wanted to identify patterns and give some impulses that can enable improvements. Now, the build instructions for Android itself are mostly commands in a shell script. So the obvious choice for us was to just go ahead and build small modular shell scripts that are then being triggered from a main script that invokes it. Also, as we saw on the previous slide, we had two Docker containers actually here that allow us to do very precise dependency management and environment control via this containerization mechanism. So, going a bit more on the details, what were our main findings? Key takeaway is this: the generic builds, the Android GSI builds, are very close to reproducibility actually, which then, as a second step, triggered our analysis of the factory images that are being flashed on the actual devices being used out there that are being published from Google. So the device builds unfortunately do exhibit quite a bit more differences. I'll come to that later. But for now, I want to have a bit of a peek at how did we quantify that? How do our metrics look? The first metric is, we call it Diff score, which is essentially just the output of diffstat. Diffstat as a tool consumes a unified diff and then tells you so many lines were added, so many lines were removed, and out of that we have a very clear numeric value. The second metric, the weight score, is essentially the fraction of files within an artifact that have had any amount of change, even if it's just a single bit. So bigger files contribute, have more impact because it's weighted by their size. I've actually brought along a very small visualization here where we can see this, where there are in the lib64 folder we have multiple artifacts, and all of these have differences, and some of them are bigger because they are larger in size. Now, what are the main findings actually on a quantitative level? And with me here I brought the visualization of our longitudinal view at multiple Android versions. So at the very top you can see Android major version. We are looking at 1 build from Android 9, 12 builds from Android 10, and 12 builds from Android 10, 12 from Android 11, and 3 from Android 12. We are mainly interested in the system image in the purple line here and visualize both the diff score and the weight score. Now, initially we can already see that we have around 200 lines of a diff score difference for Android 9, which are mainly native libraries that are not fully reproducible. With Android 10, we're nearly there in terms of reproducibility. We have some intermittent issues as well with native libraries. And with Android 11, it should be noted that these differences over here are mainly due to the Apex files that are being bundled as part of the operating system in the system image. Finally, with Android 12, at the very rightmost, we again have some issues with native libraries. So what's important to take away here is that this fluctuates a bit, but overall it is quite close in terms of reproducibility. If you want to know more on the details and the specific build numbers we actually used here, please go ahead and read our publication. We obviously have the full references for what builds these are and more details on the interpretation there. Now, moving on to the qualitative level, what have we observed here? We did a manual inspection of these differences for some select versions that we consider to be the most relevant. Actually, these were the latest versions, in fact. And here it's important to introduce a term we want to establish, the accountable builds term. We understand under that certain differences that we consider to be explainable and tolerable due to technical or organizational backgrounds. And in order to give you a better view what that entails, let's talk about Android and AOSP specifically. So with Android, we have these partition images that are then divided up, that can be decomposed further into an Apex file that represents a portion of the Android operating system that is independently updatable. And within that, we again see an APK file. And even down on that APK level, we have signatures. And that's the part where this comes in. So if you have individual artifacts that are being signed, but they are nested down many layers, then it becomes difficult to blind these signatures or ignore them for a comparison. And that's why we consider them to be an accountable change that is reasonable within this environment. Also, with Android specifically, we saw that there are property files that state certain values, like the branding names being used. It's obviously reasonable and understandable that one would have different values between a build that is being shipped by a company and one that is being built by oneself. So that is, again, something that we consider to be accountable. Also, these Apex and APK files used in Android are in fact using different prefixes depending on if you have an official factory image from Google or if you go ahead and build your own one. That's, for example, com-Android versus com-Google.Android. But that, again, is something we consider to be reasonable due to organizational reasons. However, especially with the device builds, we have also observed quite a few unaccountable differences. Most notably, native binaries exhibit differences that we cannot fully explain. It's a bit hard to explain and summarize this one because we have seen quite a selection of differences there. That can be just debug symbols, that could be that can be the symbol table, that can be the sections and the segment portion of an ELF binary. These are quite varied and would probably need to be looked at in more detail. Now, another change that we have observed is that when you build Android, you build quite a number of partitions, and one of them is always hard locked to a certain build type, even if you specify a specific one. So if you tell Android to really build a release build, in the Android terminology, a user build, a certain partition will still be built in a debug configuration that is not desirable, obviously. And then we have also observed that Apex and APK files have different content, since they actually have different versions in terms of what is claimed to be the state according to the source code and what is actually being shipped. That is, again, a bit of a trade-off, because that version difference is mostly due to the fact that Google wants to ship the latest and patched versions of components, whereas the time it was published in the source code, it was still using an older one. Now, that is a bit of the bad news. Here comes the really good news. We have actually seen quite a few improvements. So when we started out with Android 10, then Android 11, and now Android 12, we have observed that there are several areas that improved. First of all, we have the shared system image in Android 11, where we have now seen that the system X image over here has become an additional part to the overall system image, where we have vendor components that are being tightly coupled with the operating system being moved out from the main system image, and therefore we can have the platform owner Google can have full control over the system image and its reproducibility. We have also seen that bootloader images, which are used to display the specific messages during the boot up. For example, here is a message in, I think, Arabian script, where we actually see the pixel difference between the images that are being generated for the factory images and the ones that we generated. And if you overlay them, you have a pixel difference that's visualized down there. Also, we observed some more unification with regards to the actual naming of packages. Now, there are some regressions as well, but overall we see improvements, and that's the important takeaway, I guess. Finally, we did report these findings to Google, but did not receive an official clarification on most of these. So we are not fully sure in how far we influenced that, or we believe that most of that was already an undertaking that was in progress anyway. So, but still we believe it's to be meaningful to measure that state of reproducibility and how far we are along here. Overall, let me summarize. This talk and our paper is about an automation framework, SOAP, that is used for the build and analysis process of Android, which we have open sourced at GitHub, so you can check this out and try it out for yourself. In terms of our research findings, we saw that the Android GSI, the generic builds, are nearly there in terms of reproducibility, and the device builds still need quite a bit of work actually. And ultimately, we believe it to be meaningful to introduce metrics that can be used for quantifying differences in artifacts, in binary artifacts. We saw that many changes in Android are accountable, and unfortunately really have to be there for such a large software project where it's not reasonable to really achieve bit accuracy. But there are some unaccountable ones that are really worth deeper investigation. Finally, as a quick note, our publication is actually replicable on a meta level. So we've gone ahead and our analysis, our quantitative analysis, can be replicated by checking out this GitHub project, an auxiliary GitHub project, where you can go ahead and actually run the same Android builds that we did. Admittedly, it's going to take quite a bit of computation time and computation power, but you will arrive at the same figures as did the ACM reviewers, and thus we got these 3 cool badges here. Thanks a lot for your attention. Happy to take your questions.
Do you have any questions?
I'm Shananda. So first of all, great presentation. And one thing that the script is basically not Arabian, it's Bengali script. I'm from Bangladesh. So I have one question. In your methodology, you described that you extracted source code and most probably you analyzed it. So one challenging thing while analyzing Android open source code is basically some of the source codes are obfuscated. So do you think that code obfuscation will have any impact on your methodology?
Well, obfuscation in that sense, I believe, unfortunately, fortunately, with the open source part of Android, with the core AOSP project, that should not be a topic. AOSP itself is really written as an open source project, in the sense that everything there is not obfuscated in any way. Where it becomes more difficult is then the firmware for certain things, where vendors do ship components that are closed source, where you only get a binary image. And obviously there are certain areas where certain developers want to introduce obfuscated code, but as far as I'm aware, in terms of the core operating system, that's not really a topic there. It's either part of AOSP where it is open source, or it is some vendor component where they ship a binary blob. That's my understanding.
Oh, that's good. Thank you.
Hi. Name is Billy from Google Android Security. Thank you for the talk. I really like the direction of the work. I would like to get your opinion on when you do the differences analysis, right? Like, and kind of combine that with security decision. How do you, or if you were, to get a say, right? How much differences that you would detect, then you will say that, oh, maybe this is becoming something of a concern from a security point of view. And is that purely quantitative, or is there some qualitative analysis that could be coupled to aid in the security analysis overall?
Okay, so what I mainly took away here is that in terms of we consciously avoided trying to attribute like maliciousness to this code specifically, because it's really hard to just say these and these lines by themselves are more security critical than others,
right? Because
ultimately, like, a single line in certain files can be enough to completely compromise the system, and at the other times we have like these bootloader images that can explode in so many lines of difference that really are nothing in terms of security. So that becomes unfortunately really hard on a quantitative level. So that's really where the qualitative section comes in, and it cannot really be helped. But I believe so far we need to look at these reports in more detail, or probably the domain experts at Google will have to look deeper at these reports in order to gain a deeper understanding which of these differences are security relevant and which of these are just, well, nuances in the sense that they can be and should be solved, but are not safety critical.
Okay, I'll re-pull up those. You say you mentioned that you've filed those, your findings. Okay, pull them up. Thank you.
So you stole my question. It's sort of related to this. Like, I sort of felt like this notion of the accountable builds was sort of loose. It was the less quantitative part, and was curious of your thoughts on taking system policy like the SE Android policy and saying, we see differences here, but this is from a privilege, from a security point of view, that's not as important because it's a less privileged component versus over here. Because typically we think of reproducible builds, it's a small package, right? So it's not all, the hundreds of thousands of possible files inside of an Android build. So could we do something like, so for systems, there's integrity measurement architecture, IMA, and then they had policy reduced IMA based off of SE Linux policy. Could we do something similar in this sort of accountable builds, making it a bit more structured in the way we talk about the accountable builds?
That's certainly a good take, and probably worth refining on that we can use domain knowledge where we know in Android we have components that are more privileged and less privileged, and take that knowledge into account for a domain-specific definition of the accountable builds. Yes, that's actually a very, very cool idea. So that's definitely something that we could look at in future research, where we go ahead and refine that for certain areas. Because obviously that would look different than for other platforms and other complex software projects. But yeah, that's an awesome idea.
Any other questions? All right, let's thank the speaker again.